let's start today's seminar. Um, Today we're going to talk about uh, a new problem about sampling. This is also a very classical problem. It's known as sliding window sampling. So I'm going to define this problem for you first. And then I'm going to talk a little bit about its applications, why this is such an important problem. Okay. So this is a problem on data streams. Okay, stream. Okay. So what is a stream? Formally, this is defined as a sequence of elements. However, the length of the sequence is infinite. Okay, so I'm going to represent it as a using this symbol, big sigma. This is a sequence. In particular, this is an infinite sequence. Okay. Since it's a sequence, there is an ordering that makes sense, right? So I get the right to say what is the first element, what is the second element, et cetera, et cetera. So I will be using E subscript 1 to represent the first element in the sequence, E2, E3, et cetera, et cetera. Okay, so you get the idea. Okay. In computer science, oftentimes you see papers talking about problems on data streams. So typically you want to maintain a data structure. The data structure should do something non-trivial and clever about the data stream. So when you hear the word structure, it's very natural to think of data structures, right? Like binary search trees and that kind of stuff. However, one very important difference between data structures on streams and data structures in traditional scenarios is that on a stream, your data structure can only store a subset of the elements that you see. Okay. In particular, it's unacceptable for the data structure to store everything that has been received. Okay. So this is usually the main challenge. Okay. So let me repeat this. As you can see, the stream is infinite. Okay, your data structure is required to work at all times, regardless of how many elements you have received. Okay, and your data structure must be bounded in space, must be bounded in size. Okay, so you can already feel the challenge in front of you, right? So you can only retain a bounded amount of information about something infinite, and yet you will have to do something clever about this infinite thing, right? So this is the challenge. Okay, and today this non-trivial thing is sampling. Okay, so we'll see how the problem is going to be defined. Okay. So I'm going to require a notation, and this notation should be fairly straightforward. So here I put this x and y into this pair of square brackets. So this indicates a substring. Okay, so this refers to the set that goes from ex all the way to ey. Okay, so this is you can think about it as a substring or subarray. If you regard this stream as an infinite array, and then this is just a subarray. Okay, good, very nice. So I'm also going to use n to represent the number of elements that have been received. Okay, number of elements that have arrived. Okay, All right, that's fair, all right? So I give you one element at a time. I'm your enemy. I can observe what you have done, okay? And then after you are done with your processing of this incoming element, and then I'm just gonna give you another element, and you know, I'll try very hard to mess with you so that your data structure goes wrong, okay? Your goal is to make sure that you never go wrong, okay? So that's the game. So n is the number of elements that have been received, have been processed by your um, data structure. As once again, as I said, n increases indefinitely, so you can not assume that your data structure is going to take n space. Okay, so that would be horrible. Okay, good. All right, so today we're going to talk about sliding window. In particular, the problem has another parameter, so this L. So this is another integer. Um, okay, so this integer basically tells you, um, how far into the past I am interested in. Okay, so basically, I'm telling you, I will be interested in only the L most recently received elements. Okay, and with this L, we're able to define precisely what are those elements. So if you think about this substring here, n minus L plus 1, and all the way to n. Okay, so this is referred to as the so-called current sliding window. Okay, so I can tell you I'll be interested in only this sliding window. Okay, so why is it current and why is it sliding? As you can see, as soon as the value of n increases by 1, the content of this set changes. Okay, so it keeps changing. In fact, it doesn't really change very abruptly. You see what I'm saying? So every time a new element comes in, and then the oldest element in the sliding window drops out, correct? Um, so that the total number of elements in the sliding window remains L. Okay, so at all times it's a set of L. And basically, I want you to do something interesting with respect to this set of L elements. Okay, so your data structure would have to be able to do the following. So every time I do a sampling operation, you don't know when I'm going to ask you to perform this operation. Okay, so you got to be ready at all times. Okay, but every time I say, okay, here is an operation, you have to give me a uniformly random sample from the set. Okay, so basically you have to support the following operations. You have to return a uniformly random sample. By sample, I mean sample element of this set. Okay. All right. So just one random element. Okay, just one. All right. Let's start with one, and then we talk about what you could do if you want k, okay, more. Okay. All right. So that's the problem. Okay. Today, I'm not that interested in computation time. So for a data stream problem, the first priority is always to make sure you use very, very little space. Okay, space is the thing here. But in the end, I will also talk a little bit about computation time. All right. So the grand challenge here is, how much space do you need in order to support this operation? Okay. Well, one obvious and trivial solution is to, store the entire sliding window, right? You can maintain the sliding window there, right? Okay, so the good news is that you are not going to require n space, right? The bad news, on the other hand, is that you'll be needing L space. Okay, but L can be very large, right? So L can be n. You see what I'm saying? All right. So this is not a very good solution. All right. Guess what? We'll be able to solve the problem using just constant space. Just constant space. Okay. All right. So that's what we're going to get today. Okay. So this is the sliding window sampling. So why is this problem important? So first of all, an application, right? A very straightforward application. Think about Google, right? Google receives a lot of keyword queries, as we speak, right? So at the end of the day, you could say something, and not at the end of the day, that's a different problem. Let's say anytime you could say, okay, now look at what we received today, all right? And give me 1,000 random samples from the queries that we have received today, right? From all the queries we've received today. And from these 1,000 samples, clearly you're able to see the trend, right? Maybe it's about the war that is going on, or it's about something else, right? So this is one easy application of the problem. Okay. However, the significance of this problem goes way beyond that. This is actually such a fundamental problem that you will have to deal with um, in if you try to solve many other stream problems, or I should say, if you try to solve many other computer science problems on streams. Okay, this is sort of like a fundamental building brick that gives you the data support. Okay, so you can imagine when you have to deal with um, problems on streams because you are not allowed to use a lot of space, right? So techniques like sampling very naturally come in, right? So basically, the one perpetual, I would say, question that you have to be able to answer is, how can you design an algorithm that works with a random sample set from the set of stream elements that you care about? You are given such a uniformly random sample set, and what can you do about it, right? So the number one question is, how are you going to maintain this random sample set? And here it is. Okay, so here is something that you can do. Okay, all right, very nice. Before talking about this problem, let's consider a special case. This is actually something I talked about before. Um, Hopefully, you still remember it. So if I say L is infinity, well, this is a valid question, right? So I mean L can be any integer. So what if L is something super large? It's infinity. So basically, I'm saying I want the entire stream, entire set of elements that I've received so far, right? I want one random element from all these elements, right? So what can you do, right? Well, something I talked about already. Um, and remember, we want to be able to use just a constant amount of space. And we want to guarantee that this is really, really uniformly random. Okay, so no tricks played. This has to be theoretically random. Okay, so any idea? Just one word. I'm expecting just one word. One word. So that would tell me if you know or you don't know. Just one word. If you know the algorithm for solving this L infinity case, it's just one word. Everybody will say the same word. And the word it starts with an R. Okay. It's a reservoir. Okay, the reservoir sampling algorithm. Okay. So how does that algorithm work? So this algorithm works as follows. I would describe this algorithm for just one sample. Okay, because that's what we want here, right? One sample. But just so you know, this algorithm is good for maintaining any number of samples. Okay, so you could have k samples if you want. All right, but for a self-contained discussion today, suffices to talk about the case where you just want to have one sample under the case where L is infinity. Okay, so we will need reservoir later to solve a generic version of the problem. But let's first see what we can do with L is infinity, right? So in the beginning, you got E1, all right? And so what you're going to do is you will maintain, a sample. Let's call that U. Okay, you know what? Let's call that X. I'm just going to maintain just a single sample, all right? One sample, right? So in the beginning, X is just E1. Fair enough, correct? Okay, fair enough. And then you start processing the second element. So that already goes into the general case. In general, say you got EI. EI is coming in, okay? And you are maintaining X, okay? And X inductively is a uniformly random element from, let's say I instead of saying EI, I just use N, okay, EN. So X inductively is a uniformly random element from E1, E2, all the way to En minus 1, okay? So now the thing is, you want to be able to update X, okay? So what are you gonna do? What you're gonna do is you will generate a random number. Say this random number is, I don't know, R. So this random number is uniformly chosen from 1 to n. Okay, so this is something you can do, right? If R is n, and then you are going to update your X to the new element, which makes sense, right? Because this element is supposed to be sampled with how much probability? 1 over n, right? So there you go, right? Otherwise, you don't do anything. You keep the original X. Okay. Simple enough, right? So this is called reservoir sampling. Okay. So where is the reservoir, by the way? So this X is the reservoir. Okay. So remember, in general, this is good for maintaining multiple sample elements. So here, in this case, X is just 1. Okay. So that's what we're going to do. That's what we can do if L is infinity. Okay, no questions so far, right? Cool. Nice. So now let's deal with the problem for the case where L is, any number, okay? So let's look at the timeline, or I should say the sequence, okay? So here, this is the first element, standing at the first position, and so on and so forth. So what I want you to do is to conceptually cut this infinite line, okay? It's infinite, right? Because it's infinite sequence. I want you to cut it into sub-segments of length L. So remember what L is, right? So L is the sliding window length that I care about. So that's L. This is partitioning, right? So every element in the stream is covered by exactly one red segment here, right? Good. So I'm going to refer to each of these segments, these red segments, as a bucket. Okay, so I say, when I say a bucket, this is one of these red segments. Okay, so if you want very, very formal definitions of a bucket, I can give it to you. So if you look at the ith bucket, it covers, say I minus 1 times L plus 1 all the way to I times L. All right, so this is the content of the ith bucket. That's fair enough, right? Fair enough, right? So this is to remember, right? So this defines a sub-array, right? Substream, right? So this is the first element in the bucket, and this is the last one, right? You can see all these buckets are disjoint, and if you union all of them, you get back the entire stream, correct? Okay, cool. So I have to remind you that this is the timeline, and this time extends forever, which means this is infinity, right? So if you look at the progression of the stream, and then we have seen sort of like a prefix of the timeline, correct? Okay. So if you look at the position of n, still remember what n is, right? So n is the index number of the last stream element that you have received, correct? So this n will be sitting in some sort of bucket. So I mean, so you can imagine, there is so the partitioning of the timeline into buckets is done in advance. Okay, it's done in advance. And the positions of these buckets. I'm not talking about the elements inside, right? You don't know the elements in the buckets until they are received. But what I'm saying is, if you look at the definition of the bucket, right, at least the partitioning, right? So these buckets are determined in a way that is independent of the elements. All right. So I get the right to say, okay, now let's look at the last bucket. You see what I mean? The last active bucket, right? So this bucket contains the last element that has been received, and then if this is the case, and then I'll refer to it as the last active bucket. So this is the last active bucket. Okay. Oops. Okay, so formally, the last active bucket, let's use another color. Okay, so this last active bucket formally is the bucket, the only bucket that contains the last element. As you can see, there's no ambiguity here because I specify very, very clearly what are the elements inside each bucket. And there's only one bucket containing the last element. Is that all right? Okay, so this is the last active bucket. Good. Now, the word active here essentially says it contains elements that I care about. All right, it contains elements in the current sliding window. Right, good. And you have to remember that the length of the bucket is L, right? So if n is not the last element of this bucket, and then there's another bucket that can contain elements I care about, right? Elements in the current sliding window, right? So therefore, I will also pay attention to that. Okay, so formally, you have up to 2 active buckets. Okay, so this will be the second last active bucket. Okay, so in general, you can think about the last active bucket as the bucket containing n, as I defined previously, and you can think about the second last active bucket to be the bucket that precedes the last active bucket, right? So only these 2 buckets will be of interest to us. Is that all right? Okay, cool. In other words, for all the elements in the old buckets, feel free to discard them. Okay, you don't have to retain any information about them. Okay, good. Very nice. And if you want to know where is the current sliding window, and this is the current sliding window. You see what I mean? It overlaps with 2 buckets, right? Okay. All right, good. Obviously, if n is at the end of the last active bucket, and then this blue part coincides with the last active bucket precisely, so that the second last bucket temporarily becomes useless. You see what I mean? Okay, and then if you have one more element coming in, and then this second last bucket is will have to get updated, right? Because if you have one more element coming in, and then the previous last active bucket will become the second last. That's what I mean. Okay, good. Very nice. So we have two buckets here, and I'm going to I'm going to denote the last active bucket as B1. Okay, B1, and this is the second last is B2. All right, so if you look at the ordering, B1 is the most recent one. This is the rightmost one, and then B2 is the one next to it. Okay, good. Only these two buckets are interesting. Now here, I'm going to describe the data structure because the data structure is very simple. You know, I will maintain X1, which is a random sample from B1. Okay, a random element. Actually, you know what? I will describe it in another way. An element from B1 chosen uniformly at random. Fair enough. Okay, so if you look at this situation, for example, look at the blue line here. This indicates the end of the stream currently, correct? So B1 does not contain the elements that have not been received, right? So B1 contains, the beginning of the last active bucket all the way to the end of the stream here. So B1 is X1 is an element that's selected from here, uniformly at random. Okay, good. All right. And what about X2? So I will maintain another element. So this is an element from B2 chosen uniformly at random. Okay, so B2 is complete already, right? So this is B2. You know what? I'm making a video, so let's do it here. So this is B2, right? So B2 has been received completely. Okay, so this X2 is uniformly at random chosen from B2. Okay, so that's it. That's the data structure. Okay, so that is the data structure. So how much space do we need? As you can see, obviously constant. Okay, all right, cool. Well, before we talk about how to support a sampling operation, let's discuss how to maintain the data structure. Okay, I want you to maintain the data structure using only the things that I have explained to you today, which means reservoir, right? Which means reservoir, okay? So, well, the question is right in front of you. This is an interesting exercise, right? So you know the setup, okay? And you also know the goal, right? So this is the goal. All I need is X1 and X2, okay? I don't even care about computation time, even though if you know how to do things, you will realize things can be done very efficiently. But I don't really care about that, right? However, I constrain that you can use only constant space. So what can you do? Okay, what can you do? Uh-huh. All right. So you see, we have a small room here. We can make it as interactive as we want, right? So do you want to take a stab at it? Okay. So what can you do? Well, first of all, you don't have to do anything to X2, right? Just think about what happens if I give you the next element, right? So you see n, right? N elements have been received. What if I give you E m plus one, right? You have to somehow maintain X1 and X2. But I said, X2, you don't have to do anything because X2 is already a done deal. You see what I'm saying? Because it's about a bucket that has been received completely, right? So, you're not going to change X2 for sure, right? So the thing is, you have to do something to X1, right? You have to make sure that X1 remains a random sample of this B1, this bucket B1, which has been extended with just one more element, right? But if you think about it, that's precisely what reservoir can help you, right? The thing is, when I talked about the reservoir algorithm for the case of L being infinity, I said you should start applying this algorithm right from the beginning of the stream, right? Obviously, this is not something you should do here. So in order to make the story complete, the remaining bit of the story is, when do you think you should start applying the reservoir algorithm? Okay. So the answer, I hope, is clear. I hope you guys are just being shy. Okay. So the answer is obviously, at the beginning of a bucket, right? At the beginning of a bucket, right? So in retrospect, let's say this is the current situation, right? But in retrospect, you can imagine when N was here, when N was here, you see what I'm saying? When N was here. So that was the moment when bucket B2 was completely done. Okay. So X2, which is the random sample that we obtained for B2, was fixed forever already. Okay. So this is a new period, correct? This is a new bucket, right? So you want to start reservoir algorithm afresh here. So you take the first element of this bucket B1 and then you set it to this X1. Okay, so every time I give you a new element, you apply reservoirs. Okay, so you don't even have to remember the details of a reservoir. All you have to remember is that reservoir is good for maintaining a random element of all the elements that you have seen so far. Okay, but here for you, the elements that you have seen so far refer to the elements inside bucket B1. Okay, so after you put all these pieces together, I think it should be fairly obvious, what you should do, right? Okay. Once you realize this, you should also realize that it's fairly efficient, right? Because you can, every time I give you a new element, all you have to do is to apply this incremental step of a reservoir, and that takes just constant time. Okay, so this is fairly nice. Okay. All right, so now this is the big moment that everybody has been waiting for, right? So with this X1 and X2, um, how are you going to support a sampling operation? Okay, so let's talk about this here. Okay. So let's focus on the last two buckets. So this is B2 and this is B1. Okay. Now remember, B1 could be partial. Okay, B1 could be partial in the sense that this could be the end of the stream currently. And if I ask, okay, where is the sliding window currently, right? So this is the sliding window, right? So this blue part. So you're supposed to give me a random element here, the blue part, right? So remember, you only have two elements in your hands and you have discarded everything else. Okay, you don't get the right to say, hey, let's take another look at the blue portion, all right? The elements you don't keep are already discarded. Okay, you have only two elements in your hands. But the good news is if you have done things properly, X1 is guaranteed to be random, uniformly random, inside B1, inside this part basically, right? X2 is guaranteed to be uniformly random from B2. Okay, so let's see what magic um, we can do here. It turns out that the algorithm is super simple. Okay, so let me explain to you. Okay, so if you want to do sampling, okay, so this is what you do. Okay, if X2, still remember X2? X2, all right, so that's the element from B1 or B2. Look at the subscript, right? So from B2, all right, from the old bucket. Okay, so if X2 is in the sliding window, the current sliding window, that's what I mean, okay? Return x2, okay? But you do realize this if condition could get violated, right? Because x2 could be anywhere inside the bucket B2, right? So there's a chance that, it could be in here, correct? All right, so this if condition could get violated, okay? Um, so if it gets violated, you know what you can guess what you should do, right? You just return x1. So that is the sampling algorithm. I can tell you this used to be a very difficult problem.
That's what the window.
X1 cannot be, X1 would have to be within the window. Why? Because X1, this part has not come. You shall, let's not forget, right? This part has not arrived. You see what I'm saying? This is the end of the stream. All right, B1 is determined, I mean, in terms of position, right? The boundary, right? Is determined in a way that's, that has nothing to do, in a way that has nothing to do with the concrete elements of the data stream. You see what I mean? Because I can cut the line, I can cut the next year, right? So I can cut it into months. That's the idea, right? So every month is a bucket there, right? So B1 is cut, is determined in advance, and so far only this part of the stream has arrived. Okay, so X1 is definitely in here. It cannot be in here. Okay, if X1 is in here, something's terribly wrong. Okay.
You did not like specifically out. It's just
Yeah. Okay. So it's partially my fault. So that's a great question. I think I was. So when I said B1, right? When I defined B1, maybe it was too casual. I should have said B1 is the set of elements inside the last bucket that have been received, right? So that would be perfectly clear, right? Okay. Yeah. So hopefully this confusion has got clarified here, has got removed here. Is that all right? Okay. So that's the algorithm. All right. Good. Nice. All right. Small and sweet. Okay, so it's small enough. Okay, but why is it sweet? All right, so the sweet part is always the more interesting part. Okay, so now we have to go into the theory. We have to convince ourselves that this is correct. Okay, very nice. So let's just say that this X. So we have an algorithm here, right? So this algorithm is clearly a randomized algorithm. Its output is clearly a random variable because small x1 and small x2, they are both random variables, right? So this gives me the right to say, let's say x is the output of the algorithm, okay? So this x, big X here, refers to, big X here is a random variable. Is that right? Okay. So what is our goal here? So this is our goal. Say we want to prove this theorem, let's say lemma, okay? For every element in our current sliding window, we have to prove that this element gets returned with exactly the same probability. Otherwise, it's not a random sample, right? So here, for any y inside a sliding window, so you can define the sliding window mathematically like this. Okay, so fair enough, right? Okay, still remember the notations, right? So we want to prove that the probability for x being y is how much? The probability is precisely 1 over L. Okay, so this is what you want to prove. Is that all right? Okay, good. So let's do it. Okay, let's do it. Well, to be honest, at this stage, this is something you could think about by yourself. Okay, um, I could say this is the end of the seminar. I just go back to my office. Let me see. Oh well, I still have 20 minutes, so I have to I have to fill the 20 minutes. So that's basically the only reason why I'm still continuing. All right, but the point is, I'm sure this is already within your ability, all right? Just that maybe it will take you some time to land on the correct argument. Okay. So now let's do it. As you can see, there were two cases here. You can see this is the sliding window we care about, right? And I said in the lemma, you fix any element. You give me any element, okay? So there are only two cases, right? The first case is, the element is here inside B1. And the other case is the element is here, correct? Only these two cases, right? A question just to make sure we're on the same page. Do you think the element can be here? No, okay, very good. I like that. Okay, so that was very courageous. Oh, come on, you guys. All right, so the element cannot be in here because this element is an element from the sliding window, right? Good. All right, so I only have to talk about what happens here, right? So two cases. So I'll analyze these two cases separately. Let's say case one. All right, so E is inside B1. Okay, so I will prove to you for any E inside B1, the probability for X to be E is precisely 1 over L. Okay, so this L is poorly written. Okay, so it's not E here. Right? So this is 1 over L. Okay, so let's see why this is the case. Okay, good. Now, I want you to look at the algorithm and you tell me precisely the conditions for E to be returned in this case. Very good. I like that. Okay, you see, you just making progress here. I like that. Okay, so we're exactly. So this event, this X is equivalent to E1, all right? If and only if the following two conditions are satisfied, right? So the first condition is what? Is, this X2 is not in the sliding window. There's still another condition coming up, right? But this is true, right? If X2 is inside the sliding window, and then our algorithm definitely returns X2, but X2 cannot be this Y, right? Because Y is from B1. You see what I'm saying? So this condition is the first condition that must be satisfied. Agree? Okay. But this is not enough, right? There's another condition that must be satisfied, right? So the other condition says X1 will have to be precisely the element that you are talking about. Okay, good. By the way, these two conditions are independent, as you can see. Why? Because X1 and X2, they are computed in a completely independent manner, right? The X2 is about B2. All right, so when B2 is done, we start the reservoir algorithm anew, right? And whatever happened to X2 or B2 has absolutely nothing to do what's going to happen to B1, correct? Okay, so these two conditions are independent from each other. And therefore, we will have to analyze these two probabilities. Actually, we will analyze them precisely. We will calculate this probability precisely, and we will please ourselves by observing in the end that this probability turns out to be precisely 1 over L. Okay, good. All right, very nice. So now here it becomes more and more straightforward, right? So this becomes a probabilistic tutorial. Okay, so now let's look at the first condition, right? So what is the probability for X2 to fall outside the sliding window? Okay, X2 is not just an arbitrary element, right? It comes with a very strong property, right? So the property says, it has to be uniformly it has to be uniformly random in B2, right? So essentially I'm saying, okay, you take a uniformly random element from B2 and what is the probability for this element to fall in this portion. Correct? All right. And then obviously you would say, hey, let's see um, how long this portion is. Okay, so let's call this, let's call this V2. Basically, the 2 here reminds you that this is about bucket B2. Okay. And also, accordingly, I'm going to call this part U1. You see, I use U to refer to the portion that's inside the blue part. All right. V is outside the blue part, right? And also, I said U1, right? That was a typo. All right. So that should have been U2. Okay. And accordingly, I'm gonna use U1 to refer to the set of elements that are actually inside the bucket B1. All right. So this is U1. So U1, U2. Okay. U1, U2, and then V2. Right. Okay. Very nice. Hey, I want you to observe something about V2 and U1 without looking at my lecture notes there. So what can you say about V2 and U1? This is going to be extremely important later. You can see they are equally long. You see what I'm saying? This is something very important. This is why the algorithms are very clever. All right. Well, obviously you can see B2, the length is is precisely the length of the blue part. Okay, and this part is common to both, right? You take that out, and then you can see the remaining portion will have to be equally long, right? So you know V2 in size, right, is equivalent to U1. Very nice. Now let's go ahead and calculate each probability. Okay, so what is the probability of the first condition? Now you can tell me precisely, this is something everybody can do. The probability is, just the length of V2 over the length of bucket B2, which is L, right? So that's just V2 size over L. Okay, good. Now let's look at the other probability. You know what's coming your way, right? Indeed, if you look at the probability, x1 is what? X1 is a random element from U1. Okay, all right. Once again, we do not include the elements that will arrive in the future. Okay, Michelle. So it's a random element from U1. So and therefore, this is precisely the 1 over the size of U1. Okay, you get multiply. What do you get? You can see these two values, they get canceled, right? So you are left with 1 over L. And that's precisely what we are trying to prove. Good? All right. Now let's look at the other case. Okay, so I will be intentionally verbose. Okay, so I'll go for a longer argument, even though there's actually a very short way to prove it. Okay, I want to go for a longer argument for a good reason, as you will see. I want to create some comparison between the two cases. Okay, now let's look at the other case. So the other case says, okay, what if this time E is in the O bucket, right? So this means E will have to be in U2, correct? Okay, good. Well, you can still look at the algorithm and you tell me precisely the corresponding conditions that need to be satisfied for X to be E. Okay. As I said, this is a verbose. This is sort of like a detour already, right? But I think it would help to have this comparison so that you can compare them, and this is going to strengthen your understanding in both cases, actually. So you can see accordingly, X is E if and only if, again, 2 conditions are satisfied. Now this time, the first condition says what? This condition says X2 will have to be in the sliding window. Otherwise, you will be returning X1, which cannot be E in that case, right? And the other possibility is, the other condition is what? The other condition is X2 will have to be E precisely. Okay, all right. Well, now look at these 2 conditions. Unlike the 2 conditions in case 1, these 2 conditions, they are not independent. You can see, right? Because both of them are about x2. You see what I'm saying? All right. So you have to calculate. You have to calculate this probability more carefully. So let's call this right x2 in sliding window. This is the first condition, correct? Now x2 is e. That's the second condition, right? You want to calculate the probability of this conjunctive event, right? Good. So we want to apply conditional probability definition. This is something we can calculate, right? But you cannot really write, x2 b and e here because they are not independent, right? So it has to be conditional. This is always correct. And now you can calculate things easily, right? So what is the first probability? Well, this is something you know. This is just the size of U2 over L. Okay, all right. Now the second, this is a conditional probability. It says, well, given that, this x2 will have to be here, what is the probability for this x2 to be particular, to be this particular element that you have chosen from this part, correct? So x2 is uniform, right? So it will have to be uniformly distributed within this part, right? And that's the reason why you have 1 over U2 here. So that will give you 1 over L. Okay, so this creates, I would say, a healthy and useful contrast between these two cases. Now that you have understood everything, you can actually observe this probability for x, b, and e is 1 over L directly. Because x is equivalent to e, given that e is from B2, right? X equal to e if and only if x2 is e. Okay, let me repeat this, right? So this x, b, and e, if and only if x2 is e. You can easily prove this both directions, right? If and only if, right? And then immediately you jump to the conclusion that the probability for x2 to be e is precisely 1 over L. Right? But as I said, I would like to create this contrast for you so that you can compare them. Okay, you can see, okay, how come we're able to apply independence in the first case, but then we have to do something different in the second case, right? Okay. I still have 5 minutes. I'm gonna say a few things that are interesting. Well, one obviously is, what if you want to get 2 samples? Now here's just 1 sample, right? What if you want to get 2 samples? Don't try to be too creative, right? So it's something very straightforward, right? So let's be very brute force. Okay. So what would be an idea? So by 2 samples, I mean two samples, 2 independent samples. We're talking about with replacement sampling, with replacement, okay, with replacement sampling. So this says from the sliding window, I want to get 1 sample, like what we have done. And then you pretend that this sample gets replaced into the sliding window, and then we take another one. But these 2 will have to be independent. Okay, you want to get 2 independent samples from the sliding window. So what you can do is to maintain 2 copies of the data structure, right? So in general, if you want to get k samples, all you need is to maintain k copies of the structure. So if you maintain k copies, what is the amount of space that you have to use? That will be big O of k. So now let's talk a little bit about the space lower bound, right? So a natural question here is, do we really need k space in order to provide support for extracting, k samples? You see what I mean? K samples, right? So how much space do you need in order to, get k samples, right? Okay. So I'm not going to go into details, but here is the intuition why this is optimal, asymptotically. So why you indeed require k space no matter how smart you are, right? You need k-space in order to return k samples. Well, you can think about it like this, right? Suppose the sliding window is very large, much larger than k, because L can be arbitrarily large, right? Compared to k. So one element gets sampled with probability, k over L. You see what I mean? So if you think about it, what is the probability? So if you run k samples, you can actually calculate the probability that you get, let's say, k by 2 distinct elements. Because we're talking about sampling with replacement, right? So there is a possibility, you get the first sample and the second sample happens to be the same as the first one, right? But what I'm saying is this probability does not happen. I mean, this does not happen with a large probability, right? So think about it, right? So you have already chosen a sample, and then what is the next sample to fall on this particular element? So that's just 1 over L. You see what I mean? That's a very low probability, right? So the question that I asked you was that you can think about, go home, right? You can go home and think about it. Say L is very large and K remains fixed, right? So what is the probability that you will get, let's say, K by 2 distinct elements if you do K sampling operations? Okay, so the probability is very large. Okay, so because of that, and then you will see that any data structure will have to at least, store k by 2 distinct elements. Otherwise, with a very large probability, you would not be able to support the sampling operation. Okay, so this is the intuition, right? So this is the first thing that I want to talk about. Okay. Now, another thing I want to talk about is this independence requirement. Independence. So now, if you look at the timeline, right? Let's say this is the moment when we solicit a sample. Okay, you understand what I'm saying, right? So this is the moment I say, okay, give me a sample, right? Now let's say at the next timestamp after the arrival of another element, I say, okay, you give me another sample at n plus 1. These two sample elements, they are not independent. They are correlated. Okay, so this is something very, very important that you have to understand. So let me repeat this, right? So say I solicit a sample from the data structure I already explained, right? So I say, okay, give me a sample at the time of n. And then at the next timestamp, I say, give me another sample, right? So I get two samples here. And these two samples, they are not independent. You got to remember this, okay? You cannot say, well, let's apply independence over the samples to get some reliable estimate. No, it's not going to work that way, okay? So I can tell you, so this is something deeper, right? I can tell you if you take another sample, L timestamps later. You see what I'm saying? Actually, plus L, not plus L plus 1. If you take another sample here, and then the sample that you get at the timestamp of n plus L will be independent from the sample that you get at time n. Okay, so this is, to put it, in another way that is hopefully more intuitive for you. If you think about the sliding window at the time of n plus L, this is the sliding window, correct? If you look at the sliding window at n, this is a sliding window, right? You can see they are disjoint. Okay, this algorithm is called the zero overlap independence algorithm. This says if you look at two sliding windows that are disjoint, there's no overlap at all. And then you can prove, this is not trivial, but you can prove that this algorithm will return you independent samples. Okay. So in the literature, there was one very important notion. So what if I want stronger independence guarantees. Okay, what if I say that, if two sliding windows, they have an overlap, let's say K. Okay, let's use another. Instead of saying K, I would say maybe H. Okay, so let's say there's H overlap here. And what if I require the sample that I get, from these two sliding windows to be independent from each other? And then you have to try harder. There's another algorithm for that purpose. Okay, so this is something very important to bear in mind. Okay. All right. That's everything I have for today. Thank you for coming. I hope to see you again next week. Okay. All right.